And that is, by definition, b sub k plus 1. So the logic is, this is how mathematical induction works. The logic is, you assume the expression is true for a particular integer. You show that then if it holds for a particular natural number, it must hold for the next natural number. And since you show that it holds for 1, then it must be true for all numbers. So induction is what enables you to make this infinite inference from all of these. Yeah. Yo.
Can you use induction on integers too? Like go one way and then go the other? Secret base case has to be.
No one really does that. I think you asked me this question last year too. You could if you really wanted to. There are a few interesting properties that are true of the naturals that you want to also be true of the integers that you can't just wave your hand and say, but you could. But it doesn't hold, it only holds in one direction. So, I don't know. If it comes up, we'll do it. But I don't think I can't think of a time when I never really wanted to do that. Okay, good. That was induction. Some of them are harder. Should we do a hard one? All right, I prepped an example, but it might be too hard. But we can just try it. I didn't finish it. You might recall, depending on whatever class you took with me when you first learned induction, that there were these like hard proofs. The hard proofs were harder than the easy ones. The hard proofs involved inequalities. Alright, so here's a theorem that's apparently true. The infinite product, oh by the way, this is the big pi symbol. Did I teach you this? I think this comes up in like chapter, no? The big pi symbol stands for the product of a bunch. It's not an infinite product, it's just a product. So 1 minus 1 over 2 to the k is greater than or equal to 1/4 plus 1 over 2 to the n plus 1 for all n greater than or equal to 1. Okay, this is totally not obvious to me. I don't understand it at all, but apparently it's true. We're just going to prove it right now by induction. By the way, this exhibits one of the disadvantages of induction is it's not really like an understanding type situation. Usually it's you already have discovered the theorem via some intuitive means, and induction just proves that it's true. It's not really a way of discovering theorems, because you have to already know the theorem. You have to already know the proposition. All right. So I'm just going to wing this, and I hope it's just going to work out, but other people feel free to help. All right, Gossett does this proof, but he does it, in my opinion, if you're very, very smart, there are usually some shortcuts and tricks where you can just kind of like do it in the forward direction. I never do that. I do it always backwards, because that just seems easier to me. This is what I want to prove. All right, let's get started. Here's what we do. I'm going to temporarily call this term a sub n, and I'm going to temporarily call this term b sub n. And let's check to see if this is true for n equals 1. Well, I think it is, right? Because if n equals 1, this says take the product of a bunch of numbers starting with 1 and ending with 1. So this is, the left-hand side is just saying 1 minus 1 over 2. So that's just a half. And is a half greater than or equal to a fourth plus 1 over 2 to the 2? Yes. Because a half is equal to a half. Okay, so that was the so-called base case. To make the inductive hypothesis, we will suppose that this is true for some particular n. So let's suppose that a sub n is greater than or equal to b sub n for some n. And so what is it that I'm really supposing? I'm going to rewrite a sub n now without the pi symbol because I find it a little distracting. So this is, what is a sub n really? It's 1 minus 1 over 2 to the 1, so 1 minus 1/2, times 1 minus 1/4, and etc., 1 minus 1/8, all the way up to 1 minus 1 over 2 to the n. So that, I have just assumed, is greater than or equal to 1/4 plus 1 over 2 to the n plus 1. Okay. So this is what I know. I know this to be true. And now let's talk about what it is I'm going to prove. What I'm going to prove, what I hope to be able to prove, is that this holds for like the next number up, right? So I want to prove that a sub n plus 1 is greater than or equal to b sub n plus 1. And because if so, then I'd be done. Because I'd show whenever this inequality holds for a number, it holds for the next number, etc., etc. Okay, so this is what we have to do. Let's get started. So I need to show that 1 minus 1/2 times 1 minus 1/4 times, let's skip ahead, all the way up to 1 minus 1 over 2 to the n. And now a sub n plus 1 means that I take the product all the way out to the n plus first factor. So the last factor is going to be 1 minus 1 over 2 to the n plus 1. Show that this is greater than or equal to 1/4 plus 1 over 2 to the n plus 2. This is what I have to do. Okay. So how? This is my kind of like cheap way of doing this, which I really like, and hopefully it'll work in this example, is to try to make the thing that I'm trying to prove look as much like the thing that I know to be true as I can. So I'm going to take this last factor and divide by it. And so I'm going to basically rewrite my proof statement. I'm just working backwards here. And my new proof statement is 1 minus 1/2 times 1 minus 1/4. Oh, hey, you're all back. Please pass in front of the camera, thus you may experience the strange sensation of watching yourself come alive on your own.
Indeed.
We taped class for you. I can't guarantee it was the greatest class ever that you missed, but we did tape it. Can you turn the video off? Bye, internet. We went over the homework.